Okay, welcome back once again. I hope you're enjoying these. You're finding them very productive and meaningful, hopefully. If you do, and if you don't, one way or the other, give me some feedback. You notice that every time you try and load one of these screens, you always get on the top tab bar. There's a little link that says feedback. So give me a few feedback notes here, or if you want to send something in the discussions, just give me some indication of how we're going here. Whether it's good, bad, doesn't matter. If it's bad, then let me know so I can change things and make it better. And if it's good, well, that'll be all right too. All right, so here we go. We're looking at Chem3202 once again, course overview review. And we're looking at calculations involving enthalpy. So Unit 3, Section 2, Lesson 1. Here we go. Okay, some background reading on this. If you want to get the textbook perspective on calculations of enthalpy, you can go to page 643, right up to page 648. And there's a few related questions there that you can try. And once again, if you have some difficulty with these, then check the answers in the back and, you know, throw a few towards your online tutor and throw some my way if you want some help with some of these things. Okay, disregard homework postings on the bottom. I'll just wipe that out. Okay, here we go. Here are the outcomes for this lesson. All right, again, if you want to print these off, you can pause and print or write it off if you like. Here we go. Okay, calculations involving enthalpy. Now we know in the last lesson that enthalpy, of course, by itself, you could not measure enthalpy because enthalpy was referring to internal energy, all the different forms of energy and all the work that the system could do and all that stuff. In this case, we want to be able to calculate an enthalpy change, all right? So energy that was either absorbed or released by the system under constant pressure conditions, all right? And the formula that we're deriving here, or we derived last time, we said that the delta H was equal to the energy absorbed or released divided by the number of moles, because it depends on how much of the substance that you're going to involve that energy change in. So it depends on the amount. So we simply rearrange this equation to give us something a little easier to remember. Q equals N times delta H, where Q is going to be the heat absorbed or released by the system. N is the number of moles of the substance undergoing the change. And delta H, of course, is the change in enthalpy, how much energy was absorbed or released under constant pressure conditions. So many molar enthalpies are known for many, many substances in different phase changes because, of course, a mole of water anywhere is the same thing. As long as we have pure water and we're under the same conditions, the bonds when we boil water should be the same amount of energy to boil water here as it is somewhere else, as long as the pressure and conditions are the same. So for many of these things, we have tabulated values for the delta H of different processes. And there's a bunch of tables in your book on page 848, and there's a few tables in the back of your book in the appendices on page 642, 643, where you can find some of these tabulated values, these values that are already known. All right. So sometimes if you have some questions given, unless they tell you to calculate the delta H, lots of times if the process is known, you can go to these tables and find the delta H values, the change in enthalpy. So here we go. Some of the common ones we're looking at is the melting of ice, and we would refer to the melting of ice as fusion of ice. Now don't confuse that with nuclear fusion. I don't know why they use that term, but anyways they do. When we refer to the melting of ice, we're looking at the process whereby solid ice is gaining energy and it's turning into liquid water. And we call that process of melting of ice fusion. All right, some people call it melting, but the correct term is the fusion of the ice, the melting of the ice. And this is a case, of course, where bonds are being broken. We're breaking the intermolecular forces that are holding the solid crystals in place. Energy goes in, we melt ice. It takes energy. The reverse of this process is going to be known as solidification. All right, and solidification involves the reforming. So it's going to be going in the opposite direction. So the bonds are going to be reformed as the liquid water refreezes. And we know that, of course, because if we put liquid water in the fridge and we pump the energy out using a refrigerator or a freezer, energy is being removed from the water. So bonds are being reformed. So we write this in the same equation here, and you notice the double arrow is indicating that, hey, it's an equilibrium. There's a forward and there's a reverse to this. This reaction or process can easily be reversed by simply changing the energy conditions, right? Putting it in a warm environment, the ice melts. Putting the liquid water in a cold environment, we reverse the process and it refreezes. And we know that the same amount of energy is going to be involved here. So for the most part, we're saying that the value of is going to be the same for solidification and fusion because we're dealing with the same number of bonds and the same type of bonds. It's the exact same London dispersion, the exact same dipole-dipole, the exact same hydrogen bonding because it's the same water. The only difference being, of course, is the direction in which we are moving in. Okay, the direction, of course, is whether it's endothermic or exothermic. So we would write the delta H of fusion for water to be a plus 6.02 kilojoules per mole. For every 1 mole of water, it's going to take 6.02 kilojoules. And we always like to write the subscript here underneath the H to indicate, okay, we know what the process is now, it's fusion. And we know what it is we're melting water. So we like to write that under there. And likewise, if we want to reverse this, now we don't write it as a delta H of solution formation. Let me just block that out there. We don't write it as a delta H of solution formation. We just simply write it with reference to what's going on with fusion. We put a negative sign to indicate that it's the reverse of fusion. Hence, you would probably rarely see delta H of solidification ever written. We wouldn't write that like that. We would simply write it and say, well, we're going in the reverse, so we would simply write it as negative H fusion. Okay? So you'll never see solidification values. You'll always see negative H fusion, or you know that if you're trying to solidify that it's the reverse process of solidification. So there you go. In the case of vaporization and condensation, they would be opposing forces. Remember the dynamic equilibrium business? You got to have opposing forces. Forward rate equals reverse rate. In this case, vaporization would equal the rate of condensation if we were at a state of equilibrium. So in this case, we're looking at the situation whereby if we wanted to boil water, we would call that vaporization. Okay, so the boiling of water is vaporization. We're breaking the bonds within the liquid state. In order to boil water, energy has to be absorbed, and that's how much energy it takes to boil 1 mole of water. The reverse of this, if we wanted to condense the water, it would be the reverse process. Once again, same amount of energy because we're dealing with the same bonds regardless if we go forward or reverse, except that it's going to be different directions. So in the forward directions, it's endothermic. In the reverse direction, it's exothermic. Okay? So when we write this out, we would say that the delta H of VAP, so there's the process again, right? We write the VAP as the process underneath the enthalpy change for vaporization. And we also specify what it is we're vaporizing, so H2O, and we would write it here. And because it's an endothermic reaction or process, we would write this as a positive value. Energy is being absorbed. And likewise, just like we did up there with solidification, you're not going to find condensation values in any table. Really, the condensation, we would simply say, is the reverse of vaporization of water. So we would change the sign here to negative. Okay? So these are constant values. No need to memorize them, although you're going to use them quite a bit, so you probably will remember them after a while. But these values are listed on your table of specifications or your table of constants and values and formulas that you get with your public exam. All right? So double check that table there so you can find them so you know exactly where you get them. Because you never want to second guess yourself on the public exam. The values are there, so don't guess at them. Just go and get them and look them up. Okay? But any other values you need on the public exam, you can be given. They will be given to you. But if you're doing workbook problems and things like that, then you can actually go to the back of your book and look the values up. All right? So here we go. So here's a typical type of calculation you would do here with this enthalpy calculation. It says calculate the heat required to melt 50 grams of ice at 0. Now we got to watch what the question is saying because we're melting the ice at 0. There's no temperature change. So yes, they gave me the mass. Yes, I know what the substance is. So you might be tempted here to do Q equals mc delta T because we know the mass of the ice and water. We know the identity is water, so we know the specific heat value of ice. It's 2.01. The only problem is there's no temperature change. So in this question, your clue here is that Q equals mc delta T. Well, delta T is 0. It doesn't change. So I can't use that formula. So that's your key to the fact that now you're going to have to do a phase change because we're dealing with ice at 0 that's being converted to liquid water. So in this case, we would have the process here is fusion, because we've got solid water being melted to produce liquid water. So what we got to do right away is we jump on this and say, okay, let's list what we're given. We're given 50 grams of water, and we know what the process is. It's the fusion of water, so it's a plus 6.02. You notice I'm not writing down the temperature. The only reason the temperature was given in this problem was to tell you that, hey, this is the melting point of water. This is where ice is going to melt or water freezes. So that's your cue that this is what we have to use here. So the calculation itself is going to be straightforward. We say Q equals N delta H, because Q is the heat that's going to be absorbed as the ice melts. N is referring to the number of moles of the substance. Now we could easily simply substitute here because we know the number of moles equals mass over molar mass. So what I've done here is I simply substituted in for N, and I put in mass over molar mass. Now you could easily calculate the number of moles on the side if you want, and then put the number of moles in. But I just like doing it this way. Okay? So I put my values in. I'm given the mass. I know the molar mass of water. It's 1 times oxygen and 2 times hydrogen. So that's where the 18.02 comes from. That's the molar mass of water. And of course I would calculate that, keeping in mind that because this is fusion, I'm melting it, energy is being absorbed. So it's going to be a plus 6.02 kilojoules per mole. We do our little calculation, and when we do our calculation on the public exam, they like to see formulas and stuff here because they want to be able to see that the grams are going to cross out, the moles are going to cross out here, and we're going to be left with kilojoules, and that's a great value for heat. So it works out to be a plus 16.7 kilojoules, which means that there was a gain of 16.7 kilojoules when we melted 50 grams of ice. All right? We have to put heat into the ice to melt it. So there you go. That's a nice, easy calculation. May show up as a multiple choice, right? Multiple choice question, easy there. Okay, here's another one. This one says calculate the heat change that should occur when 10.4 grams of calcium chloride is formed. All right, so we got to watch this. We're doing the formation of calcium chloride from its elements at SATP conditions. So the very first thing we have to do is we have to say, well, what's the process? And the process is formation. We're forming calcium chloride from its elements. And the elements of calcium chloride are calcium metal and chlorine gas. That's calcium in its elemental form, and that's chlorine in its elemental form. So we're saying, well, yeah, that's a process that's just happened. So what's the enthalpy change? How much energy is going to be absorbed or released during this process? Well, that's one of these that you have to look up. And when you look it up on the tables on page 848, you'll find out that it's given in this notation. This is the little 0 up top here refers to SATP, or standard conditions. That's so we know exactly what temperature and pressure it was measured at. The little F is referring to the fact that, hey, this is the process. It's a formation reaction or process. And in this case, this is what we're forming, calcium chloride. And the table value for that is a negative 795.4 kilojoules for every mole that's formed. Now look at this and we say, hey, that's a negative value. So that's telling us that energy is being released. So this is very much an exothermic process. As calcium is reacting with chlorine, it's going to produce a lot of energy, and we're going to get some calcium chloride solid produced. So we want to figure out, well, okay, how much energy are we going to get if we take 10 grams? You go to the lab, you weigh out we weigh out 10.4 grams of calcium chloride. How much energy is going to be released as that's formed? So again, we write down now what we're given. We know the delta H of formation here. We found that from the table. We know the mass of calcium chloride, it's 10.4 grams. And we know now that we're going to have to calculate the number of moles of calcium chloride. So the molar mass of calcium chloride is 1 calcium, 2 chlorines, and it works out to be 110.98. And I'm simply going to draw a little box around that to get it out of the way. And now we can proceed to do our calculation. We're saying Q equals N delta H of formation, because that's the process. We substitute in for our number of moles. And again, if you wanted to do that calculation separately, you can. All right, depending how you want to do it. We put our numbers in. Okay, and again, because this is an exothermic process, make sure you carry down your negative sign here because this is going to be important. We do our calculation, and lo and behold, we've got 3 significant digits. We're doing division and multiplication, so 3 significant digits with a negative sign, which now has meaning for us. There's 74.5 kilojoules of energy, and because it's negative, that's how much energy is released when 10.4 grams of calcium chloride is formed. Okay, so not too bad. So far, so good. Here's another type of problem. It says calculate the heat change that should occur when 5 liters of propane is burned under standard conditions, SATP conditions. That's atmospheric pressure, 100 kilopascals, 101 kilopascals, and 25 degrees Celsius, so standard conditions. And we're looking at this and we're saying, do we know the process? Well, yeah, we're burning propane, so that's going to be the combustion of propane. All right, so combustion of propane is going to be propane C3H8. Remember your Chem3202. It's going to combust with oxygen to produce carbon dioxide and water vapor. Now again, this is one of these processes where the value is listed in the table because the combustion of propane is a common thing. So we know that when propane combusts, it's going to be a negative, obviously, because propane is releasing energy as it burns. And it's a quite large value. It's 23.7 kilojoules for every mole. So the question that would come up then, if this is how much energy is released for 1 mole of propane, how many moles are in 5 liters? And again, this is going to tax you a little bit because you've got to go right back to your Chem3202. We write down the delta H of combustion. That's what's given. We know our volume, and because we know our conditions now, we know the molar volume of any gas is 24.8 at SATP. This value is on your table of constants and your tables of formulas and whatnot that you get with your public exam. Go print it off and have a check and see. All right, what do we do first then? Well, we need to find the number of moles, don't we? And we're going to use the formula N equals little v, volume, over molar volume of SATP. So we put our values in. It works out to be 5 divided by 24.8 liters per mole. Okay, and that works out to be 0.2016 moles of propane. Now, we always like to keep an extra couple of significant digits as we do calculations. So I guess you keep 1 extra one, keep 2 extra ones, depending, but don't keep everything that comes in your calculator because that's going to be forever to write it down. So, in this question, we're looking for at least 2 significant digits because that's what we measured here. We've measured 5 liters, so our answer should have at least 2 significant digits. So I'm keeping a couple extra here. I'm keeping 4 in this case. If you can keep 3, that's fine too. And as we carry on down through the reaction, we're saying, all right, we know the number of moles now, so again, we do our calculation. Q equals N times the change in heat due to combustion, and we pop our values in. And once again, because this is energy release, we still carry our negative sign because that negative has meaning. And it tells us, of course, that we have 468 kilojoules of energy released when 5 liters of propane is burned. Now, my significant digits are wrong, aren't they? We need 2 significant digits because that's what we measured up here. So in order for me to put this in the correct significant digits, it's going to be negative 470. The 8 rounds up. The 0 would not be significant. Another way I could do this in terms of significant digits is I could write it as, better again, scientific notation, negative 4.7 times 10 to the 2 kilojoules. Okay? So 2 ways to do it. Be aware that you can see it sometimes. This 0 is not significant because there's no decimal place. So 470 would be 2 significant digits. 468 is 3 significant digits. We only need 2. I like doing scientific notation. No disputing how many significant digits are there. Okay, here we go again. Calculate the heat change that should occur when 4 grams of ammonium nitrate dissociates in water. And this time they're giving us the heat of solution. So the process this time is going to be the process of ammonium nitrate dissociating in water. Now that's the chemical reaction that you might have done in the lab when you did the heat of solution. We do a lab on this where we take a quantity of ammonium nitrate and we actually dissolve it in a styrofoam cup with some water, and we measure the change in temperature, which is reflective of the amount of energy change that occurs as this stuff dissociates. And believe it or not, this absorbs energy. It's an endothermic process. This is what's in ice packs and things like that. When you sprain your ankle in the gym and the teacher cracks open an ice pack, what he or she is doing is cracking open the solid pouch of ammonium nitrate, and as that dissolves in the water, it absorbs energy and you feel it being very, very cold. So we're using enthalpy to our advantage there, right? So this process, it says up above that the heat of solution formation is plus 25.7 kilojoules per mole. And if it was going to be an exothermic process, we would definitely specify that it would be a negative there. So it's definitely a positive value. It's going to absorb energy. Okay, there we go. Now we want to be able to write down what we're given and what we need to find. So we're given 4 grams of ammonium nitrate. We know the heat of solution formation. There we go. So that's how much energy is absorbed as the solution forms. That's the process. And again, in this case, we're simply looking at this and saying, all right, we know how to do this. The very first thing we want to do is get our number of moles. So N equals mass over molar mass of ammonium nitrate. So we had to calculate the molar mass of ammonium nitrate. So that's going to be 2 nitrogen. A lot of people just count it as 1, right? They forget this one. It's really 2 nitrogen. There's 4 hydrogen, and there's 3 oxygen. It works out to be 80.06 grams per mole. Our grams cross out. Works out to be 0.04996, and again, we want 3 significant digits here. So I'm going to keep an extra 1, and I'll round at the end. Once we have the number of moles, we know the delta H. The rest is easy because Q equals N delta H, and we work it in. This is a positive value, and therefore it works out to be a positive 1.28 kilojoules. There we go. And what does this mean? Well, that's how much energy was absorbed as the ammonium nitrate dissolves. Now on the public exam, when they were correcting this, what they would be looking for is you would probably get a mark for these, giving me the equation, okay, and writing in the correct delta H term. And they would also probably give you 1 mark for this and 1 mark for this. Now what they're looking for is the fact that you can write the equation, you know how to calculate the molar mass, you carry your units, this answer has a unit on it, you're doing your formulas here, you've got the correct number of significant digits, and you got the right units. So this whole business of writing out equations, some people don't do it because they say, oh, what's the point of that? I can do it anyway, so I can do it in my head, right? No, they're correcting things for process. They want you to show that you know the formulas, you know how to work them, you know how everything works in. So even though this might be real simple, the fact that that's 80.6, show it. You get marks for process. If you mess up this entirely, at least you showed that you know a little bit about what you're doing, so they can give you marks for the process, for trying. If you don't have anything written out, they're not going to give you any marks. They can't, because you don't have anything on your paper. So again, formulas, units, correct number of significant digits. Show your workings. Okay, here's another calculation. It says a 2-gram sample of methanol was burned at SATP, at standard conditions. And it says the resulting heat gain of the surroundings was 45.3 kilojoules per, well, just 45.3 kilojoules. So the surroundings got warmer. The surroundings gained energy. So this question has a little bit of a twist here. They're telling us what's going on with the surroundings, not the system. The system is actually the burning of the methanol. So why then do they tell us the heat gain of the surroundings? Well, we're looking at this and we're saying, sure, that's not a problem. We know something called the first law, don't we? All right, so here's the process. We're burning some methanol in oxygen. We get carbon dioxide and water vapor. Make sure it's balanced. We don't know the heat of combustion. You might say, well, sir, go look it up in the tables. No, they want us to show how to calculate it. All right, so that's the difference. If they wanted us to look it up in the tables, they would have said, go look in the tables. All right? They want us to actually calculate this from experimental results. So we're saying, all right, not a problem, we can do this. We're looking at this and we're saying, we know the mass of methanol that we're burning. It's 2 grams. We also know what's going on with the surroundings. You notice here, this is the heat change of the surroundings, and we said the surroundings gained positive 45.3 kilojoules. So we're saying, all right, we can do this. First law kicks in here. Actually, we've calculated the number of moles of the methanol first. Easy enough. All right, mass over molar mass for the methanol, 32.05. 1 carbon, 4 hydrogens, and an oxygen there for the molar mass. The next thing we're looking at this is saying, all right, we know how many moles we're burning. What we have to do now is apply the first law and say, yeah, if we know how much energy was absorbed by the surroundings, then that means that's how much energy was released by the system. And methanol is what we're studying, so methanol is the system. So a negative 45.3 was released by the methanol, and that's why the surroundings gained 45.3. So there we go. We've got our Q. We know it's a negative value. So Q equals N delta H. We're going to rearrange this now. We're going to rearrange this to say, all right, divide both sides by N. So let me just show you if you're not sure how to rearrange that formula. We want to get rid of N. We want delta H to be on one side, so I'm simply going to divide both sides by N. And there you go. They cross out. And I'm left with the formula delta H equals Q over N. We know Q. We know N. We plug our values in. Don't forget the negative sign. That's very important, because this is telling me now that there's a negative 725.96 kilojoules per mole released for the combustion of methanol. Now, that's not the correct number of significant digits, is it? We have to report this according to the number of units that were measured here. We measured 3 significant digits. We're doing a whole bunch of division and multiplication. So our final answer should have 3 as well, right? Because we're measuring 3. So in this particular example, I would have to round this to 3 significant digits, which would equal a negative 726 kilojoules per mole. And there we go. So that's using the system and the surroundings there. So be careful with that. All right, read the questions very carefully here. Last but not least, here's an application of a question here. This is going to make you think a little bit. Would they do this on the public exam? Well, they might, right? They want to get you thinking, and it's just a little twist. But still, you got to keep your head about yourself and say, you know, what calculations can I do here? What are they looking for? And try what you can, and you know, do the calculations that you can with the information given. You never know; you might get it worked out. But then again, think about it. It's really not that tough. All right. So in this example, we're taking a chunk of ice that's 945.6 grams, and it's going to be staying at 0 degrees Celsius. So the temperature is not changing. So we know we're dealing with a phase change. It's going to absorb 68.6 kilojoules of heat. We want to calculate the mass of ice that remains after that energy was absorbed. So what we're looking at then is we're looking at this process of fusion. We're looking at the melting of ice. So the delta H of fusion is plus 6.02. And just to draw a little picture, I like drawing pictures. Not much of an artist, but I still like to draw pictures. Here's my chunk of ice, and it's beginning to melt as it absorbs the energy. So we know that as this piece of ice begins to absorb energy, it's going to start to disappear, isn't it? And I'm going to try and wipe this out now with my white highlighter, just because I like drawing pictures. There we go. Let me just try and see if I can do this a little better. There we go. So some of the ice starts to melt here, and we're left with a chunk of ice that's a little bit smaller than it was before. And perhaps it all might melt. I don't know. But what I'm going to try and figure out here is how much ice melts with 68 kilojoules of heat energy. So I want to be able to calculate the mass. So in this question, we got what we're given, the initial mass of the ice. It's 945.6. We want to try and calculate the mass of ice that's melted. So I'm going to come back to this mass. I'm not going to use it right away. We want to figure out how much ice was melted when it absorbs this much energy. So we know how much energy was absorbed. We know how much energy is involved in the process. So what I'm looking at here is I'm saying, okay, in order for me to get the mass of ice that's melted, we need to be able to figure out the number of moles, don't we? Because N, mass equals N times the molar mass. And if I can calculate the number of moles of ice that melted, then I got this question done. And because we know Q and delta H, we can look at this and say, hey, because I know Q and delta H, I should be able to solve that problem for N. So when I rearrange this, again, if I want to solve for n, I'm simply going to divide both sides by delta H. And again, let me just show you how to rearrange that if you're not sure. I'm simply going to divide both sides by delta H of fusion. And of course, these two are going to cross out because they're on top and bottom. So my formula is going to be n equals q over delta H. I know what q is. It's a positive 68.6. I know what my delta H is. It's a positive 6.02 because it's the melting of ice. The kilojoules are going to cross out, and I'm left with moles. So 11.395 moles of ice melted. Okay, now what we got to say is, well, what mass of ice melted? Well, not a problem. We know that if we could get the number of moles, we could find the mass, couldn't we? And we do that by saying mass equals n times m of water, molar mass of water, 18.02, 1 oxygen, 2 hydrogens. There we go. It works out to be 205.3 grams of ice that melted. Hey, we started with 945. We only melted 205. How much is left? Well, subtract them, right? And there we go. So the mass of ice that remains is 740.3 grams. Okay, now the significant digits here are going to play a little role, I suppose, because in this question we're measuring three digits for the energy, and we've got 4 digits for the heat, but this guy has 1 decimal place. So let's see how that plays out. So if we measure 3 digits for the heat, technically we should have 3 here. We kept an extra 1. Here we should have 3, so this should be 205 for my mass. If I was going to round that there, 205. And down here, if I had 205 grams, then my final answer should be no decimal places. So my final answer should be 740 grams with no decimal place, because the rule of significant digits says for decimal place you go to the least number of decimal places when you add and subtract. So in this case, there's 1 decimal place. Over here, there's no decimal place. So my final answer should have no decimal place. So 740 grams. There we go. All right. Phew, a lot of problems there. Give some of these a try. All right. The only way you're going to know how to do some of these is to actually do a few. Okay. Here's some practice problems in the textbook. Again, the back of the book, the answers are at the end of the sections. You can find the answers as well. You know, if you can't get them, throw some at your tutor, and I'm sure they'll be able to help you out with this. And don't forget all the stuff we have online here that you can use to help you out with this. Old public exams, go see what types of questions they'd ask you on this. Give them a try. All right, see ya. Bye-bye.